I am Lisette Almonte, and I will be presenting our work automating the synthesis of recommender systems for modeling languages. This work was done with Sara Perez-Soler, Esther Guerra, Iván Cantador, and Juan de Lara at the Miso Group Department of Computer Science at Universidad Autónoma de Madrid. Recommender systems are increasingly used in software engineering activities. Modeling is no exception, with environments being enriched with recommender systems. However, building a recommender system from scratch requires considerable effort and specialized knowledge. We propose an automated approach to the generation of recommender systems for modeling languages. For modeling languages, users can ask for recommendations. As we can see in the video, user can ask for the recommendations and they will be added to the model automatically. Recommender systems are software tools and techniques that suggest items considered relevant for a particular user. Recommendation services are on music, video, streaming platform, e-commerce sites, and social networks, such as Spotify, YouTube, Netflix, Amazon, and Facebook. Traditional recommender systems are based on content-based similarity between users and items, user item preference, known as rating, or both sources of information via hybridization methods. In this approach, the recommender system designer will configure the recommender system via the domain-specific language called Droid. The recommender system designer will need to provide the metamodel and a set of model instances conforming to this metamodel. Using the configuration settings and the set of models, Droid trains and evaluates the different recommender systems specified via the DSL. After the recommender system designer has selected the preferred method, it will be deployed as a recommender system service where languages users can ask for recommendations via modeling clients. This listing displays a sample configuration of a recommender system for a literature scenario using UML models. From line 1 to 3, the name of the recommender is specified, as well as the metamodel and the repository containing the models conforming to the metamodel. Figure 2 shows a simplified expert of the UML metamodel being used for this case. From line 5 to 9, the target and items are being defined. For this case, we decide to define class as the target, an onEd attribute, onEd operation, and superclass as items. In a similar manner, from line 13 to 28, the identifiers for each element are being defined. For class, we define as identifier and as a primary key, the name. On the other hand, for property and operation, we define the name and the type as identifiers and also as a primary key. Also, type have been defined and identified by its name because it's not a primary type. Finally, the configuration settings for the recommendation methods are being specified. Here it's important to mention that Droid provides a wizard that can offer a recommendation set of configuration in case the recommender system designer does not have the expertise or is not interested in a fan-granted configuration. From line 31 to 35, the methods are defined. Droid supports 6 different recommendation methods at the moment. Those are item popularity, item and user-based collaborative filtering, content-based cosine similarity, and item and user-based cosine base. Additionally, collaborative filtering-based methods allow you to define different neighborhood sizes to try in order to find the best one for the current task at hand and the data provided. From line 37 to 40, the split configuration for data is defined. Split type cross-validation and random are allowed, as well as defining if the data will be split by user or by item available. Finally, from line 43 to 46, the evaluation settings are defined. Droid allows you to define several different metrics as well as different cutoff values, the maximum number of recommendations of items that would like to receive, and the relevant threshold. For metrics, we have precision. We call F1 normalized discounted cumulative gain, item space coverage, user space coverage, and mean average precision. The architecture of Droid ecosystem comprises three parts. The Droid configurator that permits the configuration, evaluation, and synthesis of the recommender system. It provides a textual DSL within the Droid editor, a recommender system synthesizer, a result view, and a recommender system evaluator that relies on external libraries, Franksys, and Vivo. The Droid service, that is a generic recommendation REST API, can be customized for our modeling languages using the configuration files generated by the recommender system synthesizer. Finally, in the client part, any modeling tool can use the Droid service to obtain recommendations and make them available to their modeling language users. Currently, our tooling supports the automatic integration of the resulting recommender system within the default tree editor that EMF provides for core-based languages. The Droid configurator shown in Figure 4 in Label 1 is an Eclipse plugin built using Xtext. It provides a wizard to create Droid projects. Additionally, as shown in Label 2, it includes autocompletion, syntax highlighting, and markers for error and warnings. Label 3 shows the generation of the Java code by Droid, but the recommender system designer does not have to look into it because Droid evaluates and provides a result view within the results of all the methods for each metric defined. The result view, as shown in Label 4, it had a color code guide showing the best methods based on the F1 value in green. The Droid service contains the Droid REST, a generic recommendation REST API implemented in Java with Jersey and Tomcat. It computes recommendations based on configuration files generated by the recommender system synthesizer. These configuration files store the trained recommender with the information of which items to suggest based on the context information. The context information is the element in the current model being developed. It also enables clients to request recommendations using a JSON-based model representation. Optional parameters are also possible, like a new maximum number of recommendations, threshold value, and item type. As shown in the motivation, we have an out-of-the-box integration into the default EMF3 editor for core-based languages. It uses model-to-text template called Java Emitter Template JET. EMF provides a set of predefined JET templates that generate Java code implemented the editor for a given core meta model. We have overridden those templates to extend the generated tree editor when a recommender pop-up menu. A list of recommended items is presented to the user, including their name, type, and rating as a choice of the recommendation. We performed two evaluations. In the first one, we would like to answer to the question, how precise and complete are the recommendations provided by Droid recommenders? To answer this question, we did an offline evaluation with the following experimental setup. We collected UML models retrieved using the March search engine with the distribution shown in the Figure 7 from the domains of the literature and education. We defined all the methods supported by Droid following a 10-fold cross-validation with a per-user technique as a splitting methodology in the neighborhood sizes of 10, 15, 20, 25, 50, and 100 for the collaborative filter-based methods. Finally, evaluating the methods with the 7 metrics of Droid and cutoff value of 5, 10, 15, and 20. Figure 8 presents the result of the experiment. In the left, we can see the methods defined as well as the neighborhood sizes. In the right, we have the different metrics specified. The results show that for both dataset using F1 value, the method user-based collaborative filtering with neighborhood size 10 is the best performing method, when a F1 value of 0.060 for the literature dataset and 0.064 for the education dataset. Considering all the metrics, the method user-based collaborative filtering neighborhood size 15 is the best performing one. It is important to mention that for this experiment, we follow the test item methodology. In this methodology, for a target user, it evaluates recommendation lists that may contain test items for all users. This explains why precision values are close to zero. Additionally, the data used have not been preprocessed. The important aspect is to consider the relevant difference of the metric values achieved by the different recommendation methods. To answer the research question 1, how precise and complete are the recommendations provided by Droid recommenders, we saw that the standard recommendation methods are able to provide sensible recommendations for every class, starting from relatively small dataset that have not been preprocessed. Results are in line with recommender systems specifically created for class diagram. We also identify aspects that will allow improving the generated recommendations, such as using larger datasets, pre-processing techniques, and incorporating more specific task-oriented recommendation methods. For the second evaluation, we did a case study on recommender system integration. We performed this case study to answer the question, how difficult it is to integrate a Droid-based recommender system with a non-Eclipse-based modeling client. For this case study, we integrated a recommender system specified with Droid into SOCIO. SOCIO allows creating models in natural language for social networks such as Telegram or Twitter. In the video, we can see SOCIO in Telegram. SOCIO interprets the sentence and shows an image of the model. SOCIO uses different commands such as undo to undo the new change and redo to redo the change. For this integration, SOCIO added a new command called recommender. When the user asks for recommendations using this command, and specifying the class that wants the recommendation for and the type of item, SOCIO sends the request to the recommender system service of Droid, and a list of items is being retrieved. The recommended item is retrieved, and the user can select the item in order to add them to the model, as the case of person, or to fix the model, as in the case of name where the type was missing. In figure 11, we can see the line of code and the number of classes in the back and front end for this integration of Droid with SOCIO. To answer the question, how difficult it is to integrate a Droid-based recommender system with a non-Eclipse-based modeling client, this case study proved that Droid-based recommender system can be easily integrated with tools as our Eclipse. Also, there is not many lines of code, and more than 50% of the code is dedicated to the user interaction. We have developed a model-based approach to automate the construction of recommender systems for model-driven engineering. It relies on a generic recommendation service. We have an out-of-the-box integration with the EMF3 editor for models. Also, we demonstrated the feasibility of its integration with non-Eclipse tools and evaluated the precision and completeness of the recommendations. In the future, we want to include pre-processing techniques for the model sets. We want to enrich recommendation context, such as including classes related to the recommendation target, and we also would like to carry out a user study to identify the strengths and weaknesses of our proposal. Thank you very much for your attention. If you have any questions, this is the moment. Also, you can find more information at droid.dsl.github.io, or you can email me at lisette.almonte@1@es. Thank you very much.